Hello, good morning, everyone. Welcome to day four for one session and design of experiments in engineering. So today we are having a resource person, Dr. A. Manmadha Chary, Associate Professor, Mechanical Engineering from IFHE Technology School, and uh, here is the short brief resume of Dr. Manmadha Chary. I know him from PhD. So we graduated both from NIT Varangal and MTech from Usman University, and he has pursued his MBE from JNTU. His research interests include 3D printing, optimization techniques, CAD/CAM, design and manufacturing of patient-specific implants. So he's much more familiar in the 3D printing area. This is something out of his interest he is presenting. So he's well known in the research community for his work done in the 3D printing area, especially biomedical implants, and he is more into patient-specific implants preparation and the problems raising, and then he is more into the medical and mechanical related aspects. So he has published more than 20 different papers in various referred journals, and he has two patents both in the US and in India. And he also received a prestigious Medic 2018 award by IIT Bombay, and he is a lifetime member of Institute of Engineers and American Society of Mechanical Engineering, and he has reviewed many reputed journals. And he is now currently working with MNR College and hospitals and the Penia Institute of Dental and Research Center for solving various critical cases through designing and manufacturing of implants. So he's more into the medical aspect of it for addressing oral and facial if I'm not taking pronouncing it
Yeah,
correctly.
yeah, oral and maxillofacial surgery.
Maxillofacial surgeries. So those related 3D printing, and he has already solved many of those issues. So it is like for taking those CAD images and then optimizing the data and all, he has used several case design of experiments techniques, and also he has improvised that using some of his techniques. And one such technique today he is going to present is about the gray relation analysis. Of course, we know a little bit about the design of experiments so far, but this is application part. This is a one case study, and the reason why we brought him is like he has a vast experience in the 3D printing, and we know today many of your research scholars are also into 3D printing and other related areas. So if at all you are trying to have this 3D printing or rapid prototyping and additive manufacturing, metal additive manufacturing and all, there is a huge scope. What we discussed earlier also, there is a huge scope in improvising the technique that is already present today. So in that regard, we have and he has proposed many models which are now successful in implementing directly in the medical area. So that's the where he is very and his experience will help us. And moreover, he is from mechanical background. So I think that will help us to understand different case studies and how he has approached with these things. And if possible, he will also share some of his patents and his experience in 3D printing and research scope as well. So the young researchers who have registered for this STTP will get benefited. And with this short note, I request Dr. Manmadha Chary to take over the session. Thank you.
Thank you, sir, for my introduction.
Thank you, sir. So I'm stopping this share so that you can
Yes, sir.
share.
I think now I can share.
Now you can. Yeah. Yes, sir. Your screen is visible. You can make it full screen.
Just
Right. Clear, sir.
yeah. Good morning to all the participants. Today, this is Dr. Manmadha Chary. Present, I'm working as a associate professor in the Department of Mechanical Engineering in ICFAI University. Okay, today I'm giving a presentation on gray relation analysis in the prestigious AICT sponsored short-term training program on design of experiments and engineering. Okay, this is my presentation outline. Okay, first I'm going to give introduction. Okay, what is the way it is using relation analysis? What is how it is using interaction analysis? Okay, where we can publish the papers, how many papers are publishing. That is I'm going to deal here. Then after I'm going to gray relation analysis. Actually, in the gray relation analysis happens so many steps. Okay, each step I'm explaining one by one. Theoretically, that is the gray relation generation, reference sequence definition, aggregation coefficient. In the aggregation coefficient, one more distribution coefficient is there. How we have to do that one, and how we have to generate the aggregation grade, and how we can determine the optimal factors for that your experimentation. That is, I'm giving the theoretically in this session. Then after, I'm going for how this aggregation analysis implement using Taguchi method. So both on this one, I'm going to deal a one case study. Okay, how we can implement these relation analysis in one case. That is, I'm going to teach here. I'm going to deliver here. Then after, in this aggregation analysis, one more method is the weight. We are giving weights for different factors. Here, instead of distribution coefficient, we are going to give some weights. How we have to give the weights of same. Okay, the same case study I'm used to apply this weights calculation method also. Yeah, that is my totally presentation. That is my outline of this presentation. Here now, okay, what is the gradation analysis? Okay, the gradation analysis used to solve the multi-factors with multi-objective functions. Yeah, that's something I think you will learn the Taguchi method, all those things. Okay, we can do only for either maximize, either minimize the case only. But some factor or some parameters having the maximization, some outputs is having the some minimization required, and that how we have to deal. Okay, that is explaining in the gradation analysis. So that on that case you can use this gradation analysis. This gradation analysis is a part of the grade system theory. So this theory is proposed by Deng in 1982. But this grade system theory is published in the Deng Zhuang in 1989. You can see this is his publication. Nearly almost 5,171 citations are there. Just I will share you how he's published. Actually, this is the main and paper. That means the base paper of this gradation analysis. You can see here. This is the gradation system theory. Okay, in this gradation system theory, one is the gradation analysis. He is the Deng Zhuang. He's a engineer in automation systems. Okay, he's from China. Okay, he's a published paper based on, you can see here. The just I'm giving just outlook here. Okay, here gradation space. How where we can utilize, that is he's explained this. Then after grade generation space, and how we have to generate the grade. These all you can see. This is the theoretical one. This is the mathematical basic functions you can see here. But as an engineer, we are using the application of this gray system. This, you are seeing the so many statistical methods nowadays we are using. Actually, that is belongs to the that is theoretically it is the statistics. Theoretically, it is the mathematical calculations. But the application of mathematics, application of statistics, we are using to deal the optimization of the our experiments or optimization of our results. Gray modeling, how we have to do modeling. That means how we have to generate the equation based on our systems. Okay, this is the mathematical this mathematical calculation based on the matrices. Next, okay, here by using we can do the forecasting. Right? How we can predict the experiments, how we can predict the values. So because of this gray forecasting method, nowadays, okay, this is using in the economics also. In climate changing also, they are using this gray relation analysis. The gray series forecasting. The series means okay in the interval how it is changing. That is also you can predict in this method. And seasonal climatic prediction. That means okay, this okay by using this gradation analysis, You can find the total optimal value and some particular time how it is changing the response, and in particular interval how it is changing the response. That also you can predict by using this gradation analysis. But that is the major advantage of this gradation analysis. Okay, now here topology prediction. Okay, okay, even nowadays the topology optimization is very important to reduce the material in the design stage. So that also we can deal in this relation analysis. Systematic prediction. Okay, here like this one. Okay, in the great strategy situation. Okay, how we can predict the situation. Decision making of groups. How again in particular group how we can decide it. Let's suppose in the human resource HR persons are there, how they have to predict the persons, how they can predict the that means behavior of this clusters. Okay, that means a group of people. But that also we can do by using this gradation analysis. That's why okay, this gradation system is very popular. Is not in mechanical. Is it popular in so other industry also? Okay, this is a great programming. Okay, how we have they based on this gray programming, some softwares are working. Okay, that's why nowadays okay this gradation system is using in the artificial intelligence and the data system also. Okay, gray prediction control. Okay, how we can control the values. How we can okay that means that's why so we are using the control system. Okay, in the control you can see this is the control system diagram. Here they are predicting the behavior of the control system. So that also is possible by using this gradation analysis. You can see here, okay, because of this gradation analysis having so many applications you can use, and okay, you can use in the different field. Okay, this using your gradation analysis, you can predict the values in the entire the value and the entire the system you can check, and in particular season or time and some particular area also you can predict the values and you can forecast the values and you can give the one conclusion and whatever you require, that means optimization or conclusion or prediction, everything you can do by using this gradation analysis. So that's why this is very more popular, not in mechanical, in all the industries. Okay, even medical science also, even it also in so many industries are using. So you can see some examples I'm giving to you. This gradation analysis is used in agriculture and environment. Okay, in agriculture, they are predicting the growth of the trees based on our the previous data. That also they are is going on. Environmental condition. Okay, where okay how we can, the predictive of this changes data changing, that also is possible. And earthquakes and economics. Okay, nowadays in the economics and marketing also they are using, and in the manufacturing industry also, in the material science and power systems. There is electronic people using, mechanical engineers are using, and that means economics people also using. The normally civil people, agriculture people, you can take in a different field. This is using the gradation analysis. So that's why it is very popular uh, in predicting the gradation analysis. You can see a small. I'm giving to you how many journals are publishing and how many journals are there. Yeah, that is you can see here. Okay, this data is taken from the science directory. Just yesterday I've searched based on the gradation analysis that when I'm using the keyword, you can see how many journals are published here. You can see almost all 15,121 journals are published based on this gradation analysis. Even okay, 2020, this many journals are published. And the next year also, okay, some journals they are publishing. They are given the volumes in this 2021 also. You can see here, okay, the growth of the publishers using this gradation analysis is increasing day by day. So that's why you can use this gradation analysis in your research, okay, in your calculation, in your prediction, in your forecasting, in your seasonal changing of the attributes, and everything you can uh, precast, and that means forecast and identification and automation. Everything is possible by using the gauge analysis. Here, this is data is taken from the Springer. Okay, you can see here. Just I'm searching the gradation analysis. You can see almost 4,900 chapters are there. Okay, this then 4,398 papers are published. These conference papers are published. Okay, so many papers are published. Nearly 9,000 papers are published still now here. Where even computer science also they are using, because okay in the, artificial intelligence you can see here, and the artificial intelligence this relation analysis using to predict the values. Okay, in the engineering sector, in the medicine and public health also they are using nowadays gradation. The social science also, and business management to make a decision, to take a decision, okay, to predict the economic and to forecast the future economics. That also is possible by using this gradation analysis. So that's why you can see how many papers are published in this field. Okay, this gradation analysis is using in every field. Okay, here artificial intelligence are using, the mechanical systems also using. But nowadays, okay, majorly in the artificial intelligence in the computer systems. Nowadays, computer system in the computer science, artificial intelligence is a major role. Okay, it is a booming area. Okay, but how we have to give the intelligence artificially? They have to forecast, and they have to forecast that value, and they have to give to the that particular program that particular things. Okay, that how we have to forecast, how we have to identify before coming to that one. So that is possible by using the gradation analysis. In the mechanical engineering, already okay, we are going to optimize the values, okay, for reducing the machine cost, or some reducing the material cost, something, anything. But we are minimizing the cost, or minimizing the time, or minimizing the something, and for our improving our mechanical systems. That's purpose we are using this mechanical engineering in industrial and production engineering also. You can see the information system also nowadays they are using to control the control systems. That means the control systems values. Okay, that purpose they are using this gradation analysis. The computer engineering in the CAD/CAM system also they are using to develop code. Okay, where we are using some extrude revolve options in our CAD, but in the internally it is having so many codes are running. Okay, that in that, okay, they are using this gradation analysis also. Okay, here that's why I'm giving this list. Okay, okay, how many papers are published, okay, where it is publishing, okay, how where it is using, you can check here based on this result. Nowadays, okay, I'm taking some premier journals. Okay, in the emerald, okay, this many journals, 1208 journals are published. So in the sage you can see here 6454 journals are published here. Okay, the Wiley publications 9214 journals are published. Okay, here our ultimate goal, we have to publish a paper, and that means we have to use the optimization techniques, we have to improve our systems. Based on our results, we have to publish a paper. And that is our goal as a researcher. Okay, here, okay, okay, you can see. These many journals are publishing in these publishers. So that's why this gradation analysis is very popular, and this is you can use in your research. You can see a list of journals. You can see okay, these are the mechanical engineering journals. Here they are. These journals they are having the some aim and scope is there, and then aim and scope they are giving some automation techniques with using the gauge analysis also. Okay, these are the mechanical journals. These are the electronics journals. Okay, and the cybernetic and power systems and automatic systems also they are using this gauge analysis. You can see in the control systems also here. This one. Okay, they are using in the mathematics. This one, the mathematics also they are using these gradation systems, and biomechanical systems also they are using. The civil engineers are using, and the operation research also they are used here. And this is the pollution controlling purpose and fuel processing technology. You can see here. From this you can extract. The gradation analysis is not only for the mechanical engineering people. Okay, this gradation analysis is using in each and every field to optimize the values, to predict the values, to forecast the values based on our on your previous data. But okay, we are having some data. How we have to do the gradation analysis? How we can optimize the values? How we are using? Okay, here that is I'm going to explain here. The gradation analysis, okay, still now, okay, there is no particular software. That means, okay, suppose in the uh, mini tab is there, you can see the Taguchi methods, you can do it. Suppose design expert is there, you can see the RSM, response surface method, you can see something in the different optimization techniques having the different softwares. But these gradation analysis are not having a single particular software because of this the vast area. Okay, they are using the different people. So that's why to predict all those things to for one software is not enough. So that's why still now, okay, for the gradation analysis, okay, a particularly suitable software is not available in the industry. Okay, but we have to go for the calculation, and we have to do some calculation. Then you can predict the values. You can forecast the values. You can optimize the values based on your data. Here, how we have to do the calculation. Okay, I will explain you one by one here. In the gradation analysis, okay, we are having only these 5 steps we have to do here. First one, gradation generation. From gradation generation, we have to go for the sequence references. Okay, how we have to be doing the sequences. From this one, they are going to find the gradation coefficient. From this gradation coefficient, they are going for the gradation grade. Based on the gradation grade, they are going for the optimal values. These are the steps to do gradation analysis. So here, how they are doing the gradation generation. Okay, you can see here. So majorly, okay, this gradation analysis used to different optimization values. The base, okay, some one is the maximum, one is the minimum, and both are maximum, both are minimum. And okay, one is maximum, another two. Suppose you are using the 3 output factors. One is maximum, two is the minimum, and that also you can use. Okay, so different inputs and different outputs either may be maximized, either may be minimized. Okay, whatever the condition is there, and that we can use. First, before going to gradation analysis, first we have to do the gradation generation. In the gradation generation, they are using to for the normalization. So what is the normalization? Okay, in the normalization means the values we are going to the we are the maximum to maximum and minimum values we are taking together, and they are giving some particular range. Okay, you already what are the statistical normalization. Here also, okay, here we are going to do some normalization based on your data. How you have to do the normalization? Okay, these are the formulas you can see here. Suppose I require the small is the better criteria. Suppose, okay, I'm doing some experimentation. Okay, so my output is the roughness. Always the roughness you should minimize it when you are doing some manufacturing. So that's why I'm using the smaller the criteria using I'm here. So here the formula is xik, that means for this one to generate the xik value, we are taking the maximum. Okay, in the totally, suppose I'm doing some 9 experiments. From the 9 experiments, okay, what is the maximum of the roughness value we have to take here, and maximum value, and the minimum value from that 9 experiments you have to take it, and each experiment, how whatever the value is there, that value you have to take it, and you have to calculate it for the normalizing of that particular output response. Okay, this is the formula. Okay, from one particular column, that means one particular response. Okay, whatever the maximum value, whatever the minimum value they are taking, and that value they are using for particular experiments. So that's why here the values are going to normalizing here. So that's why these formulas are using here. The smaller is the better. That's why I'm using the maximum value. Something I require the larger is the better thing. Suppose some higher hardness value, okay, some tensile strength is there. I require the high tensile strength for a particular material. So whatever my output, whatever which factor we are required higher strength. So higher strength means that is the larger is the better criteria. So that's why here we are using this formula here. Okay, that how they are doing this value, how they are calculating this value. Okay, from the particular column, that means from the totally particular experiments, whatever the maximum value is there, that is you have to take it here. Whatever the minimum value is there, whatever the minimum value is there, that value you have to take it here. Then okay, for that particular experiment, for each experiment, okay, based on your data, you have to calculate the normalizing value by using these formulas. Okay, okay, here for that particular suppose second experiment is there. The second experiment strength value minus in total. Suppose you are using the 9 experiments. From the total 9 experiments, whatever the minimum value is there, that is you have to take here. Whatever the maximum value is there, that is you have to take it here. Then you can get the normalized value for particular experiments. Okay, here the smallest the better criteria means on that case we are using the maximum value. Okay, the larger is the better criteria case we are using the minimum value. So that's why it is going to normalizing. Okay, in the gradation analysis, one of the major advantages, we can predict the target value. Okay, we suppose some I require some target. Okay, in the marketing, they are using some market target values. Okay, suppose particular year. Okay, we have to reach this much sales. Okay, for that how we have to do. Okay, whatever the input we have to take, that is calculating based on this gradation analysis. In that case, we are using the target value here. So suppose I'm using the 10 years data. From the 10 years data, okay, from the 10 years, what is the maximum sales are there? What are the minimum sales are there? And whatever the target sales are required. That is you have to take and you have to calculate. Then okay, and then they are going to do some calculation to get the prediction and to get the target. So on that case, they are using this formula. Okay, here these are the okay, from this one they are using the normalizing. After normalizing, okay, now we have to go for the reference sequences. In the reference sequences, the total values they are doing they are performing the value, they are fixing the value from 0 to 1. Okay, yeah, different values are there. So that different values they are setting from the 0 to 1. Okay, so that purpose they are using some formulas here. X naught k minus xik. So x naught k they are fixing the 1, and xik whatever that particular experiment how much value is there, that is they are taking, and the modulus of value they are taking as a reference sequence. Okay, here from the normalizing value you are getting the values. From that normalizing value, the values they are fixing in 0 to 1. Okay, so what are they doing? So very big values they are taking the small values by using these reference sequences. Thereafter they are going to calculate the variation coefficient. Okay, in the gradation coefficient they are calculating the coefficients based on the reference sequence values here. Okay, whatever the reference sequence value is, the delta 0 I. Okay, based on the delta 0 I values, they are calculating the gradation coefficients. So when are calculating, okay, in the some particular experiments, okay, what is the minimum gradation reference sequence is there, that is they are using, and maximum reference sequence is there, that is they are here using. And for particular experiment, suppose I am taking the 9 experiments. From the 9 experiments, the minimum reference sequence I am taking here, the maximum reference sequence I am taking here, and for a particular experiment, suppose I am using for the gradation, I am calculating the gradation coefficient for the second experiment. So I am taking the second experiment value here. Okay, here from the 9 experiment, what is the maximum? Here I am using here. What is the minimum? I am using here. Then I am calculating the gradation coefficients. So from the normal, okay, from the reference sequence, we are setting here 0 to 1. Thereafter, we are comparing here in this case. So that's why we are using the gradation coefficient. Okay, here in the when we are calculating here, we have to fix one distribution coefficient. So once again, we have to fix the 0 to 1. So that's why we have to give some distribution coefficient. Here, from the distribution coefficient, we are giving maximum 0.5. Okay, this value is proposed by the Deng. Okay, whatever the theory is proposed. But nowadays, some researchers they are calculating this distribution coefficient by using the entropy methods and different methods. The popular method is the entropy method. Okay, that is we are discussing in the after completing this normal gradation analysis. How they are calculating to that this entropy values to do the gradation analysis, or instead of this distribution coefficient. So that is, I will explain after this method. So then after calculating the gradation coefficient, okay, here, okay, why we are using this distribution function as a 0.5? Suppose, okay, nowadays almost all they are using the 0.5 only. Suppose you can use, suppose 0.2 and 0.3. Suppose you can see here. Okay, the range is just changing, but the sequence is same. Okay, suppose this, you can see this line and this line and this line. Okay, these are the three distribution coefficients here. Okay, the gradation coefficients using the three distribution coefficients. Suppose I am using the 0.3 here for this experiment. Okay, you can get the distribution coefficient I'm using here. You can see for this total for the 9 experiments. Okay, this is the graph. Suppose I'm using the different distribution coefficients. Suppose I'm using. Okay, this is the graph. Okay, I'm using another distribution coefficient. This is the graph. For the all experiments having the same gradation coefficient, but okay, the values are changing, but the order are same. So that's why, because of this conclusion, nowadays almost all the researchers, they are using the single value 0.5. Yeah, but some researchers, they are not agree with, because okay, the output value, some parameters, some output value is influencing more, some output value influencing less. So some output is required higher, that is on that one where some the influence is more. So on that case, we can't give same distribution coefficient for the all. So they are giving the different values. So for that particular case, okay, they are using the entropy method. Okay, that is we will discuss next. But in this case, in the normal gradation analysis, the distribution coefficient they are using the 0.5. You can use the 0.2. You can use the 1 or so. From 0 to 1, you can use any value. Not a big issue. Just here, okay, the graph is okay. You can see here the gradation coefficient values are changing, but but the all, when I'm considering the all experiment, the same distribution coefficient, where the gradation coefficients also same, but only the values or space is changing. Okay, here you can see here this much deviation is occurring, but okay, the sequence and the relation is same. So from this conclusion, we can take only 0.5. You can take anything 0 to 1. Okay, that is suggested by the Deng theory, the gradation systems. Okay, from this gradation coefficient, they are doing the average. Okay, suppose for the 9 experiments, okay, they are calculating the gradation coefficient. Thereafter, for the okay, they are taking the average value. Okay, from that, they are telling the gradation grade. Okay, how they are doing, I will explain once again. Okay, suppose okay, roughness value is there. Okay, they from that, okay, they got some distribution coefficient. Suppose strength is there. For that, one more distribution coefficient is there. So here, now in this case, we are doing the average of this both values of the this coefficient value, this gradation coefficient value. Then they are predicting a gradation grade. If in this gradation grade, whatever the maximum value is coming from the 9 experiments, okay, whatever the maximum value is there, that maximum value they are taking the good result. That means they are predicting that is the optimal value. That is the procedure. Here, these are the values. These are the formulas they are using to calculate the gradation analysis. So here, in the gradation analysis, they just okay, we can do only optimization only. But how we have to conduct the experiments? Okay, from the data you can predict the data. Okay, you can do the optimization. But okay, how to data generate in the manufacturing industry? Suppose in the economics in the economics side, they are taking the previous data and they are doing some optimization. They are applying the previous whatever the formulas are there. This formulas they are applying, then they are predicting the value. But when we are coming for the manufacturing industry, suppose okay, we have to do some experiments. From that experiments, we are giving some optimization value. So here, okay, that's why we are using the Taguchi method. Not Taguchi method, you can use the RSM method. Okay, anything you can do. Okay, the experiments, based on the experiments, you can do the optimization by using the gradation analysis. But here, okay, the for your understanding easily, for your understanding, I'm taking the Taguchi method. Okay, the Taguchi method. Okay, he's proposed the Dengi Taguchi, the Taguchi method. Okay, from the Taguchi method, we can do only single performance characteristics. That means, okay, maybe you can do for maximum max value. That means maybe the totally you can do the maximum is the better criteria, and that only you can do the optimization. The minimum is the better criteria, and that only you can do the optimization. But when we are taking this gradation analysis from that experiments, you can do the best value, maybe maximum and maybe minimize. You can combine the both. Okay, whatever the flexibility is the flexibility is required, that you can adopt by using the gradation analysis. So in this gradation analysis, the multi-functions, the multi-characteristics is going to single response character value. That means the multi-responses is taking together and generating the single response. From that single response, you are taking a optimal results. Okay, that is doing the gradation analysis. Okay, this is the flow chart how to do the optimization technique by using this this Taguchi method. Okay, from the Taguchi method, now just we are doing the experimental design. Okay, in the Taguchi method, you know, I think you are studying or learn. Okay, from this Taguchi method, okay, from the different parameters with the different levels, you can get the experimental setup. Suppose 3 parameters, 3 levels are there. Maybe you can get the 27 experiments. Maybe you can get the 9 experiments. The 27 experiments, that's the full factorial. 9 experiments means half factorial. Okay, that is given the theory based on the Taguchi. Here, from that, okay, they are making the signal to noise ratio. Okay, suppose one single response is there, then do the calculation easy. Suppose the multi responses are there. From the multi response, okay, how we have to predict the value? On that case, we are using gradation analysis. Okay, the gradation analysis, okay, first, okay, gradation generation. Already, this is this is we are discussed just now how we have to do the gradation generation. Then they are going for the reference sequencing. After from the reference sequence, they are going for the gradation coefficient. From the gradation coefficient, they are going to for the gradation grade. From the gradation grade, so whatever the maximum value you are getting from the maximized value experiment, okay, is saying the optimal value from the all the experiments. Okay, that you can give the conclusion. Here, now I'm taking a single or a small case study. Okay, here, suppose I want to do some implant. When I'm going to implant, I want to take the CT images of the patient. Okay, because the patient specific implants, okay, the dimension should be perfectly matched to the patient. So individual patient have the unique dimensions. So different persons have the different dimensions. Okay. Yeah, so that's why. Okay, now in this case, okay, we have to get the dimension from the CT images. But when we are taking the CT images, some dimensional deviation is occurring in the dico images compared to the patient. So when we are going to implant, when we are designing the implant, that implant is not matching to the patients perfectly. So that's why still now, okay, this medical in the medical community, where the implantation is lagging in the IT manufacturing process. Yeah, okay. That's why they are doing some okay, they are predicting how much deviation is there. Okay, that much deviation they are giving some factorial value in some particular companies. But okay, when I'm taking the CT images, you have to get the proper results. Okay, suppose okay, when I'm taking the good results, okay, just means I'm using the higher energy, I'm getting the accurate dimensions, but the radiation dose is increasing to the patient. As a medical community people, okay, that is not accepting. So we have to reduce the radiation dose, and okay, we have to improve the accuracy of the CT image. That is required when we are going to manufacturing a patient specific implant. And here, some cases you are getting some image noise. Image noise means, so, okay, you can see here sometimes here the white value, some white hole you can see. Okay, some on that case, it is getting some noise because of the current changing and when we're doing the CT scan. So here, okay, here what is going on when I'm taking the CT images? Okay, we should reduce the noise and improvise the. Okay, we should reduce the this noise also, improve the accuracy. So here, two minimize value is there, one maximize value is required. So on that case, we are going to use the gradation analysis. Okay, this is a practical problem you can see here. With this the manufacturer of this city manufacturer, they are given the manual, and that manual we are seeing on that. Okay, some optimal values also there. They are when they are releasing the machine, they did the optimization techniques. Okay, which part, which values you have to set in your machine. They are given the data in the manual, but when they are taking the experimentation, they are considered only radiation dose only. Okay, after completing my experiments, we are observed. But okay, as a medical community people, they have to reduce the radiation dose. Okay, this accuracy is not necessary because just they are printing, they are giving this type of films. The radiologist just they are checking, but they are not measuring the dimensions. But when we are doing the implant, you should take the proper. That means you should take the accurate images. Then you can get the accurate implant when we are designing. So as a mechanical engineering, we require the accurate data images. So as a medical community, they require only shape, and they have to reduce the radiation dose. So here, so that's why once again we did the experiments how we have to get the good accurate images with less radiation dose. So that's why we are used to some this gradation analysis by using the Taguchi method. But how we have to do the experimentation? That's why we are using the Taguchi method to find the experimental setup. From that experimental value, we did the optimization by using the gradation analysis. From the gradation analysis, we find the optimal value. From that optimal value, we are given the one conclusion. So normally when we are doing the implantation, this is a sequence. First, we have to take the city images. From the city images, you have to do some design, then go for the STL file. In the STL file, okay, before going to manufacturing, you have to do some simulation, whether it is withstanding or not, how much load is bearing, that everything you have to calculate. From then it is okay, go for the manufacturing. Okay, after manufacturing also you have to test it. Okay, our simulation results is validating on the implant or not. If it is okay, go for the surgery. This is a sequence. But at the starting, we are having some problem to get the CT images in the CT scanner. So that's cases. Okay, we are taking the optimization techniques in this case. Here, this is not necessary for you. Just I'm giving small instruction. So when the X-rays are passing, okay, suppose this is the object. When the X-rays are passing from here to here, some energy is taking here. Actually, here the X-ray tube is there. The X-ray tube is giving the. Okay, here you can see. Here this X-ray tube is there. Here the detector is there. Suppose here we require some tissues. If the CT scanner is giving the X-ray beams and it is detecting the beams. Okay, some energy is taking the object. Okay, this energy is exactly not taking here. Due to this deviation, you are getting the inaccuracy. Okay, this when we are observing this energy, it is converting the radiation dose to the patient. So when we are reducing the radiation dose, okay, this image is not getting properly. Okay, actually we require this object. Okay, I'm taking this off part. Okay, actually we require this shape, but instead of this shape, we are getting this much shape, this shape only. So this deviation is there. This deviation we are considering as a dimension error. That is called the beam hardening effect, as per radio technology, radiology terminology. The image noise, already some noise is getting in some, means the noise means it is a standard deviation of the that is the, it is measured as the standard deviation of voxel value in homogeneous quantum. The quantum is some tissue. In the tissue, when we are creating, okay, it is taking the pixel. Okay, normally when I'm taking the photo, it is taking the pixel, but when I'm taking here image, it is taking the voxel. Pixel is the two-dimensional element, voxel is the three-dimensional element. Okay, on that, okay, some X-ray photons are taking for that particular value, it is deviating. So that's why you are getting the image noise. The radiation dose means some of the energy is absorbed to the body. So when we are getting the higher radiation dose, maybe the DNA will be break. So you have to reduce the radiation dose. How they are calculating this beam hardening correction? Okay, the beam hardening effect we are calculated by the beam hardening correction factor. This is the output energy. This is the input energy. This energy means when I'm taking the CT scanner, we are using the voltage, tube current, and time. Okay, voltage, tube current, time we have taken. When I'm taking the image noise, okay, this is the formula we have to take the standard deviation. Okay, sigma is equal to k by under root of z into c into t. Z is the slice thickness, c is the tube current, t is the time. So here also current is there. So when I take the radiation dose, okay, this is the value. Okay, this is the pitch. So whatever the in our mechanical engineering, the pitch is using in our system. Same here also, the pitch we are calculating. Okay, the distance traveled per one revolution. Okay, here the X-ray beam is traveling like this one here. Same when we are moving the nut, same, okay, how it is moving inside of the bolt. Same thing here also. The X-ray beam is rotating like in the spherical motion. Okay, we can define same thing here, pitch. In our mechanical system, we are taking the two successive parts distance, we are considering the pitch. But in the medical community, they are taking the distance per one revolution per beam width, how much beam width is there, and on that particular one revolution, how much distance is traveling. Based on that, they are calculating the pitch. So here, there is a pitch is there. So your tube voltage current is there, here current is there, here pitch is there. So that's why we are considering the input three input parameters. One is the tube voltage, and there is the tube current, and there is the pitch. Okay, like this, you have to decide the factors, which factors are affecting from, okay, that affected factors you have to consider as the input parameters. Okay, that is the design of express. Okay, from this one, okay, we are decided these three input parameters is playing a vital role. The three input parameters we are considered as the input parameters for doing this experimentation. So what do you require here? We require the maximize the beam hardening correction factor. So here, this output energy, input energy. Okay, it should be 1. Okay, there is no loss. It is 0 means it is so much loss is there. So we require the maximum value here. So that's why here I'm taking the maximize the beam hardening correction factor is required. Minimize the image noise. We should minimize the image noise, and we should minimize the radiation dose. Here 1 is the maximum, 2 is the minimum conditions are there. So that's why we are taking the gradation analysis. From by using the normal diagnostic method, we can't. And these, okay, the gradation analysis using in the medical community also. When we are publishing the paper, the medical people also, they can easily understood when we are writing the paper. So that also one of the reason to select the gradation analysis for particular this case study. Okay, from this case study, I published one paper. I will explain. I will show to you after completing this all the calculations. Here, these three parameters, these three output values, we are taking the single function, making using the gradation analysis. Okay, for this one, okay, we are taking a one mandible here. Okay, we have to do some scanning, but when we are doing the normally human, we can't calculate exact dimension how much deviation is there in the dimensional. So that's why, okay, the dry mandible is taken from the Usmania General Hospital. And okay, we are this pant. Okay, this is whatever the dry mandible is there. That is we are one shape, okay, that is representing as a phantom. Okay, we are cleaning in the mechanical cleaning we did, and we are this one we are boiled for fat removal purpose. Suppose fats also there, okay, maybe it is changing the threshold in the CT scanner. Maybe the dimensional may be changed. So that's why we have taken only bone in the CT scan also. For taking the different human tissues purpose, they are selecting the different values. Suppose if you are doing for the only normal bone CT scanning, okay, they are setting the different values. Suppose you are taking for the angiography. Suppose you have to take some nerves to extract some nerves from your body. There is the different parameters to make a CT scanning. So my case, we have to go for the metal implants to store the bone implant, bone part. So that's why I'm taking the bone as a phantom to do the calculations. So okay, when I'm walking here, okay, we are considering this is the x-axis, this is the y-axis, this is the z-axis. So same here, the same x, y, z axis we are used to make a experimentation. Okay, this phantom we are kept here. We did some experimentation by using these values. Okay, we are taking the tube voltage, tube current, and pitch. And the tube voltage we are taking the 80. And okay, always when we are considering the input parameters, you have to take the uh, the intervals are same. Okay, that is the main condition to take the level in the parameters. In each parameter, suppose I am taking the 80, 100, 120. Okay, here the difference is 20. Here is the difference is 20. And when I'm taking the tube current, okay, 300, 400, 500. So 100, 100, 100 is there. When I'm taking the pitch, okay, this, okay, here is there. But here 0.5 to 0.9, almost here 4 is there, here 3 is there. So but okay, in CT scan only these 3 pitches are available to change in the CT scanning. So that's why we are taking these parameters. But almost all this average value, this average value, this. So this you should consider when you are doing the experimentation in your result, in your thesis, in your research. So from the L9 orthogonal array, okay, we are extracted this design of experiments. Okay, we can go for the to L27. Okay, 27 experiments we can do, but each scanning, okay, they are charging 3,000 rupees. So 27 means 27 into 3. How much is there? We nearly 1 lakh, something above 1 lakh. So that's why we are taking only 9 experiments, 9 into 3, 27,000, because these are less compared to 1 lakh. So that's why we are taking 9 experiments. It is a you know, there's a fractional factor. Okay, that's for half factor. So that is the major advantage of this orthogonal array. This is a Taguchi method. Okay, here this is 120, 300, 0.516. These values is there based on the manual of the CTE scanner vendors. Okay, remaining these experiments also we did based on L9 orthogonal array. Okay, thereafter we are we model the CAD model based on the CT images of the bone. Okay, whatever the bone is there here, is totally this diamondable. We are made a CAD model based on the dico images in the Mimic software by using the matching cubic algorithm. Okay, here so many algorithms are available in this one. Here we are using only matching cubic algorithm. From that matching cubic algorithm, we did this CAD modeling. Okay, here we are identifying some landmarks. Okay, to measure. Okay, how we are measuring the how we are calculating the measurement difference. Okay, we are taking the measurements of the diamondable. We are taking the measurements of the CAD model. Okay, the difference between these two measurements, we are considering the error. Okay, when we are calculating the beam hardening correction factor, we are taking the CAD model dimension by diamondable dimensions. So that is we are considering. Okay, actually that is a beam hardening correction factor or the definition as per medical community, the output energy by input energy when we are considering the CT scan. So here the output is the CAD model. So input is the diamondable. So the output the CAD model dimension by diamondable dimensions were taken to calculate the beam hardening correction factor here in this case. So these are the landmarks. These landmarks are taken and to calculate the difference, to calculate the linear distances. Okay, these are also, okay, you can see some CDL to CDL. Okay, these are the some landmarks. Okay, this is taken from the medical community. They are having some already existed landmarks are there. Already existed lengths, or that means already these definitions are available and medical community anatomy books. Okay, from that, okay, we are taken here this length. Okay, from here to here, they are representing as a bicornular width. Okay, from here to here, they are calling as a bicornuite width. From here to here, or that side MA to this side MA, they are taking this GO to GO. Here to here, they are taking the diagonal width. Okay, here like this some terminology is available in the medical community. Based on this the terminology, we identify the linear dimensions. Okay, this is I'm taking the x-axis dimensions. This I'm taking the y-axis dimensions. This I'm taking the z-axis dimensions. When we are doing the scanning, in the each axis also having a different variation is observed. So that's why we are taking the three individual dimensions we are taken to calculate the dimensional error. Okay. Now, okay, the diamondable length we are calculated by the normal digital caliper. This is uneven shape. Okay, we can't use a CMM also. So that's why we are taking that this digital caliper. And these dimensions, the CAD model dimensions, we are measured by using the CAD modeling object. Okay. Now we are calculated the beam hardening correction factor here. Okay, this is x-axis dimension, this is the y-axis dimension, this is the z-axis. In each axis, we are taking the two dimensions. And here is the diamondable dimensions already is there. This is a CAD model. This CAD model to the diamondable, okay, whatever the ratio is there, that is we are taking and we are fixing as a beam hardening correction factor. Okay, this is x, y, and z axis. Okay, now I'm taking okay, that is okay. How we have to take the measurement of image noise? Image noise. Okay, here this is a formula is there. Okay, here we are taking the 300, 400, 500 voltages. And okay, when the time is constant for all the experiments, we are set at the 0.4. The slice thickness, when we are taking the CT scanning, we are taking the 0.625 mm for each slice, and the K is the constant. Okay, that's the measured constant. Okay, the measured constant is a bone. Okay, it is having 1.06 value. So that is I'm taking here consider. Then we are calculating the image noise. The radiation dose. Okay, in the CT scanner, okay, they are giving the report directly in the radiation dose. Okay, the milligrays. Okay, CTD value. The milligrays. The radiation dose is measuring by the milligrays MGY. Okay, these values. Okay, this is automatically CT scanner is giving the output value. And this image noise and this beam hardening correction factor, you have to calculate whatever you have seen. Okay, now here, okay, these are the 9 experiments. From the 9 experiments, we are taking the beam hardening correction factor X, Y, Z. So from here, we are taking the average value, and whatever the average value, that is, we are considering the beam hardening correction factor for the particular experiment. So this is a dimensional error. Okay, this much dimensional error you are observed in this case. This is the image noise. This is the radiation dose. See, okay, the seed here. We can observe, okay, in this case, the image noise is, okay, it is repeating 0.057, 0.055. Once again, it is repeating here. Once again, it is repeating here. All here, the only tube current only changing the parameters. So that's why it is repeating here in this case. Now, when I'm giving the optimal solution by using these results, I'm doing any optimization. I'm not any optimization techniques. Just I'm drawing a plot. From this, you can say which one is the better. Suppose beam hardening correction factor will require the maximum value. So where you are getting, suppose I'm taking this average beam hardening correction factor. Okay, this is one. Where I'm getting the maximum value here, I'm going to go the fourth, not fourth. Here the 7th experiment, it is getting the maximum value here. When I'm taking the image noise, we should reduce the image noise. So that means the 3rd experiment, 6th experiment, 9th experiment is giving the minimum noise. Here is 7th experiment is showing. Here 369 is this showing. So how you can give the conclusion? Which fact? Okay, okay. What is the optimal experiment? What is the optimal solution for this one? Suppose I'm taking the radiation dose, the graph. Okay, you can see the minimum radiation dose coming in the seventh experiment. So from the beam Honey correction factor, image noise is good, but what about the image noise? So we can't predict, we can't give a proper conclusion for the for these three results. So that's why we did the optimization technique by using the gradation analysis. For these three individual outputs, we are making a single output by using the gradation analysis. So that's why we are using the gradation analysis. Already you know these are the formulas. Okay, based on these formulas, we are going to calculate here. Okay, these are input parameters. These are output parameters. Okay, these are experiments. Okay, so each parameter, whatever the beam Honey correction, okay, this for here you have to go for the normalizing value. So here, that value you have to set here. So ideal value I'm taking the 1. So 0.2417. How is coming this one? By using this formula. Maximum yik minus yik5, maximum yik minus minimum yik. So here I'm taking the beam Honey correction factor here. Suppose I'm taking image this radiation dose I'm taking. Here whatever the maximum value is there here, 41.61 is the maximum value. Here the minimum value is 2.23 when we are considering this 9 experiments. So here one is missed here. So 9 experiments are there. 9 experiments. Okay. Okay, here for the maximum value I'm taking 41.61. The minimum value I'm taking the 7.14. So suppose I'm calculating the 7th experiment normalization value. So on that case, okay, maximum yik. So I'm taking the 41.61 minus 34.61. I'm calculating the normalizing value for the second experiment. So that's why I'm taking this value by maximum value 41.61 minus minimum value 2.23. So this is I'm taken to do the normalizing value. So from the maximum to minimum, the maximum and minimum values, we are taking some to do some normalizing. That means the maximum to minimum, we are taking some simple solution. So that's why we are taking this normalizing value. Same thing. So here we require the minimum value. So that's why I'm taking here. So for the larger is the better criteria, you have to take this formula. So by using this two formula, they are calculated, and the calculated value you can see here, this one. So here the ideal sequence is 1. Okay, we require the 1. Okay, I'm in the previous theory I'm explaining to you. We have to set the values from 0 to 1. So that's why we are doing the normalizing value. Okay, you can see here the minimum is the 0, the maximum is the 1. Okay, in between of these values are all the values are there. Okay, when we are using that formula, you can set the values from 0 to 1. So from this one you can get this is the maximized, this is the minimized value. Same things on image noise also. Okay, from that formula we are calculated, and the results are shown here. Same here. Here we are calculate the normalizing value. So that is given by gradation generation. Okay, here we did the gradation generation. Thereafter you go for the deviation sequence. The deviation sequence means here the 1. Okay, we are taking the 1 is the ideal condition, and from 1 minus this value 0.2417. Whatever the value is there, that value they are keeping here. Okay, the theory I already explained to you in the previous slides. The formulas. Once again, I will show it to you here. Xjk minus xjk, xik. So this is I'm taking here 1 minus that particular value. 1 minus that particular experiment value. Like that you have to do to calculate the deviation sequence. Okay, one minus this value, you are getting this one. Same thing, 1 minus this one, you are getting this one. Same like that, the beam honey correction factor, the image noise, and CTD value, that is the deviation dose. For these three output values, we did the deviation sequence based on this formula. Thereafter, go for the gradation coefficient. The gradation coefficient, already you know what is the gradation coefficient. Where there is a formula, you can see here, this is a formula. The delta mean, okay, here already you did. Here that is a delta mean means here the deviation sequence. You can see that the deviation sequence you are calculated. Delta 0 I. Okay, what is the minimum value here? Suppose 0 is the minimum, maximum is the 1. In between, you have to set it. So same formula I'm taking, delta mean plus sigma, that means the distribution coefficient here, plus delta maximum. For that particular experiment value, plus maximum value. Here the distribution coefficient, we are taking the 0.5 because okay, why we are taking? Okay, we are taking the maximize and minimize both we require the same. So that's why for the 0.5 I'm given. So half of factor I'm given for each output. So that's why I'm selected here 0.5, and you got this gradation coefficient for the beam honey correction factor for the first experiment. Same way the second experiment, third experiment, like that they are doing here. These are the formula here. The bottom is there. Okay, it's not showing. Okay. Thereafter, okay, for the this is a gradation coefficient you got for the three output parameters. From this three output parameters gradation coefficient, we did the average. Okay, that is taken as a gradation grade. You can see here this average value, this one, this average value, this one. Okay, now the three output parameters optimal value, we did the single optimal value by generating the gradation grade. Okay, this is a formula already you can see here. This is the formula. Okay, the gradation coefficient to average value, you are consider the gradation grade. From the gradation grade, you can predict the optimal value. So you can see here what is the maximum value from this 9 experiments. Okay, this is the maximum value. So 0.9483. Here this is the minimum. So this is a worst actually. This is a very bad. So that's why we are getting a bad results. But when we are taking only image noise, okay, only for the ratios, these are good. So that's why they are taken here. So we are compared the default values. This one 120, 300, 0.5. So how much time taken for the scan time? 2.3 seconds is taken. Okay, here the optimal value when I'm taking this 1.5 seconds is taken when we're doing a calculation. The time we are minimizing means automatically the observed energy also minimized. So that's why we can reduce the radiation dose in the patient. So now you can see 25.86 milligauss, we are reduced to 4.82 milligauss. Okay, this much difference we are reduced. Nearly 20 milligauss values we can minimize it when we are using these optimal values. Same thing, image noise also. The volume also we are reduced. Dimension also we reduced. Beam correction factor reduced. Okay, here we are observed. Okay, in the CT scanner, they did the optimization, but they are not did the multi-factor or this multi-object optimization. They not did. Just they did only for the single object function only. So that's why we are used to this methodology, and we are claimed okay these are the parameters are good. So that's why okay we are publishing one paper. This one here, the measurement in the 2017 when I'm doing the PhD in NIT Warangal, we are publishing one paper here based on this calculation. Here you can see here what I'm explaining in theory, and still now here you can see all those things. This formulas, how we have to calculate the this beam penetration factor and image radiation dose, all those things. Okay, still now how many members are did in the experimentation, that is we are written in the background. Oh, the image noise. Okay, now we did this is the input parameters. In each parameter, this is the factors. From it, we did the align array. Then we did the experimentation. Then we did the CAD modeling here from this mandible to here. Then after we have calculated the beam height correction factor and image noise, radiation dose. Then after we applied this gradation analysis. This deviation sequence gradation generation. Then lastly, you got the optimal values, gradation grade. Okay, this is a good results. Here, you know already, okay, which factor is influencing. So tube voltage is more influence value. Okay, I think this is ANOVA test. I think maybe some of research person is explaining to you. I'm not explaining to. Okay, from this all these input parameters, which one is playing a major role to optimize the value, or major role in the explanation, that is telling the response value, that is an influence factor. So tube voltage is getting more to response, then after getting the tube current, then after pitch. So based on the energy only, this error is coming. So if giving the higher energy, we are getting the higher radiation dose. So when we are giving the less energy, we are giving the less accuracy in the CT images. So that's why we did the optimization. That based on the optimization value, we are claimed, okay, this much 20.4% image noise is increased, and the radiation dose also we are reduced 22.5%, and dimension error also almost 7.5% reduced. Okay, instead of 2 mm error is there in the previously, now we are getting up to 0.51 mm. The 2 mm is not a big issue for the medical community, just that printing they are giving. But for manufacturing a single implant, very accuracy is required, 0.5 mm, because the CAD model you are having the 2 mm error. When we are going for the manufacturing in the manufacturing implant in the IV manufacturing, once in you are getting 2 mm error, 2 plus 2, 4 mm. Okay, instead of the suppose your mandible, suppose your implant having the 10 mm, suppose a small implant they are using. So what happened, instead of 10 mm, it is going to 3 mm. When you are fixing to the patient, it is not fixing properly. So that's why, okay, this results we did this optimization, and based on this results, we got the better implants. Okay, from this one, we calculated the equations, okay, for the beam hardening correction factor and image noise, radiation dose, and what is the dimension error. Okay, from this you can calculate without doing any experiments. Okay, I did only 27 experiments, so I want the remaining 27 experiment values, so that you can do that, you can calculate by using these formulas. Okay, you can generate the ANOVA also. From this you can so many ANOVA, you know, analysis of variancy to predict the influence factors. Okay, here this is the tube from the ANOVA, so we get 60. This is the high influence factor for the tube voltage. After tube current, this is the pitch. The error is this much. So almost 98% confidence level. Okay, these experimental values is suitable. Is almost 98% accuracy level is there when we are making a experimentation. That is, we are claimed by using this one. Okay, these are my results. Okay, now here you just here I'm explaining to you in the distribution coefficient I'm taking only 0.5, but some of the people they are not satisfying to take a 0.5. Okay, here in the 1949, okay, the entropy method is given to change the distribution coefficients in the 1949, okay, by the Shannon and Weaver. But this entropy method is used in the gradation analysis to find the distribution coefficients. Okay, always, okay, okay, our prediction values are not good. Suppose I am considering, okay, the input or the output parameters, the equally I am given the weightage. So sometimes I am not given the equal weightage. Suppose high, or suppose some output parameters having the more influence, so I will give 0.9. Suppose some in output or some output parameters giving the very less influence, I am taking the 0.1. So like that you can give. But where we have to give the 0.9, where we have to give the 0.1, okay, that you don't know. So that values is giving the entropy method. Okay, this entropy method is the objective data. That means automatically you can calculate the entropy values. So for that one, okay, these are some few steps are there. And that is, I will explain to you here. Okay, first we have to calculate the D sub x. Sorry. Here gradation coefficients. Now here in the previous case, from the gradation coefficient, here this gradation coefficients we are taken. The gradation coefficients we are going for to calculate the gradation grade. Directly we are taken for these gradation coefficients are used to find the weights. So that is we are going to deal in the entropy method. Almost on the gradation analysis, only two variations are there. Everything is similar. So for that, okay, this is gradation coefficients are there. This gradation coefficients they are taking the summation from that. Then after they are taking some normal over this EJ value. That means entropy characteristics. Okay, that this is a formula sigma k sigma I2 I1 to M. Okay, M is the output values. How many output values? Then W weight function and this gradation grade for each experiment for the total experiment of the gradation case. Suppose I'm calculating the second experiment entropy value. You have to take the second experiment coefficient by all the experiments gradation coefficients values. And this is WE. They are calculating x into E 1 minus x plus 1 minus x into EX. So these formulas they are using. X means Rij by dj. Whatever the value is there, this value here, this from this gradation coefficients they are taking, that value is taking to calculate the WE weight function here. From this weight function, they are generating the entropy function. The K is equal to 1 minus e power of 0.1 minus 1 into M. Here the M is the number of experiments here. The number of experiments, suppose here I am taking the 9 experiments, you can take only 9 here. E to 0.5 minus 1, this is a value, you are getting this much value. So that value you have to take it. Then after, this is the entropy you are taking, the total sum of the entropy, how much you are taking, that is you have to calculate. From that, you have to calculate the each response weight. Okay, that is you are calculating by using this function. Each is 1 minus n minus e, 1 minus ej. Okay, ej value, this is you can see here, this one. Sorry, here this one. And 1 minus n. N is the number of response. Here M is the number of experiments. N is the number of output response. I am taking here 3. So here you have to take 3 minus E. Whatever this value is coming, the summation of this entropy. This E. That is you have to take it. Okay. By total summation for all the experiments. Whatever the value is there, that is you have to take. Suppose I am doing the second experiment too. Wait, okay, you are taking the second experiment value EJ, then total values you have to calculate. Then after from this one, you have to do some gradation grade. For this is the entropy value. For that entropy value, you have to take for the gradation coefficient and you have to multiply. Then you can get the gradation grade. These are the formulas. So here up to gradation grade coefficient, you have to use same formulas whatever I explained in the previous. To find the distribution coefficient, here we are using the entropy method. Okay, these are the formulas. The same okay problem I'm taking to calculate this entropy method here in this case. The same gradation coefficients I'm taking. This is the gradation grade is same. Okay, here the 9th exponent is getting the result. So when I'm taking the entropy method also, I'm getting the same one. Okay, I will show to you. Okay, this gradation coefficient value I'm taking from this gradation coefficients. Okay, I'm taking the calculate the dj d sub g. That means the sum of gradation coefficients. So this totally summation, how much is coming, that value here. For the imaginary totally gradation coefficient, whatever the summation is, that is I'm represented here. Okay, this is the summation value I'm represented here. Thereafter, we have go for the evaluation of the normalized coefficient. K is equal 1 by e power of 0.1 minus 1 into m. M is the number of exponents. Here I'm taking the 9 exponents, so that's why I'm taking the 9. So the K value I'm calculated as 0.1713. So here this K value I'm taking to calculate the entropy of each response here. So Ri J by dj, something this per coefficient. For suppose beam Honey correction factor for the first experiment, this is the value of the patient grade for 0.3974. That is taken, but total gradation coefficient average value. Sorry. This is one. So this by this one I am taking here. That is I am representing as a entropy quality factor. Same thing for the beam Honey correction factor and for the image noise for the irradiation dose. That is we are calculated based on this formula. Thereafter, we are calculating the entropy for each experiment. Kw into Rij by dj. Okay, this is already we are calculating this value. We have to take the We. The W weight function already is there. Okay, weight function is you can see here is a weight function here. X e 1 minus x. Okay, here x means Rij dj. Okay, this is the function. In this function, so we are applied these values. Then you are getting these values here. You can see K into We. K already we are taken. Okay, the K value here 0.1713. That is we are substituted here. And We Ri suffix j dj. This totally function we are taking here. This one. Okay. Now okay, and because of now we have taken the previous values, these values, and these values you are substituted in this equation. Now you are getting the weight for each experiment here. You can see here. So if you want, I will show you how you are calculated. This is some Excel sheet. This is the gradation grades already is there. Okay, this one by this. Okay, this is the summation. The gradation grade summation I'm taking A1 by this one. Something. Okay, for this the beam Honey correction factor. This is the image loss. This is the ratio dose. Thereafter, we are taking the formula. This is the function. Based on this formula, okay, this is the K value. This is the whatever the entropy function is there on that entropy function. This is taken. Okay, based on this formula, we are calculating this values. And that is you can see here. Now we calculate some of the entropy. For the individual entropy you are taken, the entropy is used to calculate the gradation coefficient or grade. Okay, now here the totally okay whatever the this each individual entropy is there. The summation I'm taken. You can see here the summation of here these values I'm taken and I'm showing here these are here values. From this one, okay, once again you have to calculate the weight for each response. Okay, this is a function 1 minus ne into 1 minus ej. This is the value. Okay, n is the output response. Here I'm taking the 3. E is this value. Okay, here this for the beam Honey correction factor E value. And here for the each individual response ej value. That is okay, these values. Here for the experiment, for the first experiment, the beam Honey correction factor, this one. This value you have to substitute here. For the first one. For the second value, you have to substitute this value. Like that, when we are doing, you will get this function. That is, you can see here. Okay, now here, after doing this one, okay, now gradation grade. So here, this is the weight function. Okay, these weight functions, okay, already this, the formula to get the gradation grade. This weight function, you have to multiply with the gradation coefficients. This is the Rij value. So from this one, you got the weight functions for the each experiment for the each output value, and this weight function you have to calculate the gradation coefficients. Then you are getting the total gradation grade. So this one multiplication of this one. So when we are doing this one, lastly you are getting for each experiment gradation grade. So in the previous case, just we are taken only 0.5. But you can see here the weights we are given individually for individual experiment. How they are calculated based on this entropy method. Okay, these are the mathematically we are giving here. Analytically we are giving here. The previously, okay, in the previous case, just we are assumption, okay, based on the gradation system theory, just we are taking the 0.5. Nowadays, okay, this method also using to give the weights for the gradation grade calculation for the individual experiments. They are giving the individual weights for each output values. So then after they are calculating, they are getting this results. Okay, this results you are getting. This is then after, okay, this when you are doing this, they are got this results. Now they are doing this summation, and they are getting this value summation. Okay, for the each experiment they are doing the first experiment. What is the gradation grade? Okay, this summation. The second experiment, like this one, you can see. So in this one, the maximum value you are getting here. So that means this is the optimal value. Okay, that is the optimal gradation grade. Okay, that based on the gradation grade, you can say this is the optimal value for the your experiments. For the 9th experiment, good. So you can see here when we are calculating the weights for each experiment with using the entropy method. Without calculating anything, just we are applying just a distribution of 0.5. Almost all you are getting the same results. So that's why, okay, you can use this one, this first method. But when we are predicting very high accurate one, suppose in the economics persons, okay, their prediction is very important. So their distribution coefficient for each variable they are considering in the individually, and for the each variable they are giving the some weights individually. So that's why this is using. For our mechanical systems, this first method is good, I am thinking. Okay, some of the people, they are considering the weights with the entropy method by using the different values. You can see this one. And these values, okay, without taking any gradation grade coefficients from the directly whatever outputs is there, from that output you can calculate this by entropy method and to calculate the gradation grade. In the previous case, we are taken the gradation coefficients. From the gradation coefficients, we are calculated the gradation grade with using the entropy method to assign the weights for individual experiments. But okay, here without calculating any gradation grade, just for the output also, you can generate the gradation grade with using the entropy method to assign the different values for each experiment using this formulas. Okay, this is also third method they are using. Okay, directly, okay, they are taking the output of some experiment. Okay, I'm taking the first experiment. Okay, I'm taking the 10 experiments for the first experiment value by summation of all the experiment value. That is taking the Pij. Then after they are getting Pij into ln Pij. The logarithm values they are taking, and the k they are taking k value. The k is equal to, I'm taking 1 by ln m. M is the number of experiments, I think. Yeah, m is the number of experiments. M is the number of experiments. Then after they are considering the degree of the divergence. Okay, that is they are calculating 1 minus Ej. This value entropy fraction. From that one, they are calculating the weights. This weights and this the coefficients. Then they are calculating the gradation grades. So this is another method. Okay, actually this method I am not giving any case study. Okay, but here also this is also method also using. Okay, to find the gradation analysis, majorly we are using these three methods. You can take any paper, any research paper in any community. Only these three methods are using to find the optimal value in using the gradation analysis. First one, normal gradation analysis. Second one, gradation analysis to find the weights using the entropy method. Third one, using the gradation grade entropy with the normal values without taking the gradation quotients. These three methods are using still now. Okay, these are my references. Here, the major advantage here, suppose you are taking the weights of so many output values out there, so many weights are taking. Okay, the weights is summation of the weights is greater than the 1.5. Suppose when you are generating the equation, or something like that one here, you can see that. I'm generating this equation by using the gradation generation here. But suppose weights is more than 1.5. Okay, this equation is not suitable. Always, okay, this equation is equal to what I'm doing. But when I'm taking the weights more than 1.11, so this equation is not suitable for your experiments. That is a major drawback when we are using this entropy method. So that's why nowadays in the top see so many different algorithms are using for the assigning the weights for the each output. Okay, these are my references. Okay, from this papers and from this relations theory, I explained to you. Thanks for your attention. If any queries there, you can ask now. If any questions, if any queries.
Okay. Thank you, Dr. Manmadha, Chary. I think we can now take up if you have any doubts. Those who are into this gray relation analysis and their papers, I think they will have a better idea from starting till ending how to carry out this experimentation and then move it for the gray relation analysis for multi-objective. Yeah.
Yes, sir.
So that is the main thing here. So
Yeah.
if anyone has already used it, or if they have any problem statement which comprises of two different type of objective functions, which is like sir was mentioning about, one may be increase higher the better, another one may be lower the better, and then decision has to be made which one to choose based on some weights. So if you already have such weights over the other, then I think you will have a better understanding, and the better judgment also can be made using this. So if anyone has any doubts, they can ask. The floor is open for discussion now. Please unmute and you can ask. Oh, okay. You can.
I think no question.
They are lost in the Excel, I suppose. But that's what is needed. Like when you compare your paper and when you have shown that in the Excel sheet, I think the Excel sheet will give us direct results. So I think this is the part where most of them they will be able to get it, and this is what is needed now. If any of the researchers, if they want to carry out this type of analysis, and when they look into the journal papers, and Manmadha paper is also available, so if they look at that paper, the backend Excel sheet, they can do hand calculation on their own for one set and apply the same thing for their problem statement. I think most of the things will be sorted out. And since you have given a very good example of different types of the differentiators that we take, like suppose 0.52 is generally what is given in the papers. Yeah. So even during my this thing also I struggled, and then later on, like you have rightly pointed out, we found like we need not restrict that to 0.5. It can be anything value for 1.1 to 1. So it doesn't matter. Only thing is it differentiates, and that's what is
Yeah.
needed.
Yeah, that's why I'm showing that graph also.
Yeah, yeah. So for all those who are into this design of experiments, then they have selected the Taguchi design layout, and then after they have conducted the experimentation, suppose they have responses which is not one, and so far we have conducted all the shown examples are only one responses, but suppose they have two or more responses, and which is fine. And if they need to have a comparison between these two or more, then they need to make a decision based on the weights, and that is where our gray relation analysis will work very well, and that's what is shown very clearly by Chary sir.
How to do the weight optimization, how when they are giving the weights, how do the calculation also. I'm giving the presentation.
Right. And that entropy is also very important, because normally it will be done randomly, or sometimes we impose. Then we need to give lots of justification figuring out why these weights are selected. And people may agree or may not agree. But entropy way, I think it is a very easy to give justification when it comes to publications.
Suppose you're publishing one papers, maybe the reviewer asks how you have to choose them like that, or that bad. On that case, when you are doing this type of mathematical calculation, based on that mathematical calculation, you can assign the entropy. That is a good.
Okay, so if any other has anything to clarify, of course you sir has already posted the mail, so if you have any doubts, you can directly post in his to his email account, and he will be more than happy to help you out. And let me share the today's feedback, and in the meantime, okay, I'll do that even through WhatsApp. So I'll share the feedback link through WhatsApp, and if nothing is there, okay, we can end the session. If anyone wants to say anything. All right. So I take this opportunity to thank Dr. Manmadha Chary for taking time out and then giving us a detailed discussion on gray relation analysis. And I think it is first presentation on specific to gray relation analysis. Most of his lectures I have seen, it's morely detailed to 3D printing, bioimplants, additive manufacturing. So this is the first of its kind, I suppose, and I think that's maybe the other reason why the presentation is more into medical implants and other things. But that is what is needed.
My intention is how mechanical engineering working in the medical community with our using our tools, with optimization techniques.
True.
That's why I'm sure this paper.
Yeah. So that is needed.
This is essay journals. 2 years back.
Yeah. Okay, sir. Thank you very much. Thank you for taking time out and giving us this lecture.
I especially can I talk 1 minute? Especially thanks to team of this ASAT program, and I'm special thanks to Dr. Varun Kumar to giving this opportunity to present my research topic of the gauging data analysis. Thanks for this opportunity.
Thank you, sir. Thank you.
Sir.
Bye.
Yeah. Actually, I'm hoping some questions maybe is there, so that's why I prepared.
But I think no one has done in the gray. They are happy with Taguchi, and they have stopped with Taguchi, I suppose. And this is a interesting area. They'll realize this once they get into the experimentation, and once they try to give 2 different entities and then bring that under one justification, then it's a problem. Like MRR and surface roughness, we struggled a lot to go for one parameter approach.
Yeah.
So this is a interesting thing, and I think we don't have to do much of the tools also. Like you
Yeah,
don't
no,
have
no,
to
no.
learn.
Till now, there is no particular tool for the creation
No,
analysis.
no. What I meant is like we don't have to use genetic algorithm or
Yeah,
learn
mm,
other evolutionary algorithms for solving these kind of problems. It is very
yeah,
easy, straightforward,
yeah,
and it's statistically proven and approved. So
yeah.
I
Approved.
think, yeah.
I'm
So
shown the first slide. Nearly 5,000 citations are there for the field.
true, true.
Yeah.
Yes, sir. Okay, sir. If they
Okay.
have any doubts, they'll get back to us
Yeah. Thank you, sir.
through
Thank
mail.
you.
Thank you, sir.
Once again, thank you.
Thank you. Bye. So this next session starts at 1:30, and this will be by Dr. Vijay Kumar, who is assistant professor from NIT Varangal, and he'll be discussing on another case study on TOPSIS, using the TOPSIS technique and other things. So do join us at 1:30 sharp. Okay, thank you all. I'm ending the session now, and I'll be leaving the feedback link in the WhatsApp group. Okay, thank you.